So in this lesson, we're going to expound upon what we talked about last time, which was the prompt radiation from a nuclear weapon. Now, this is going to be a long video. So I'm going to divide it into three different sections, and I'll have the timestamps below the video to show where you can jump ahead. Now, the first section is going to talk about radiation damage to biology. The second section, we're going to look at, well, we know there's prompt radiation coming off of our nuclear weapon. So how do we characterize that? How do we figure out what kind of neutron and gamma fluxes, or numbers of particles per second per centimeter squared, are we going to be looking at? And then finally, we're going to see how does that correlate directly with dose to biologic systems, and then what can we do to mitigate that? Something like the old duck in cover, where you hide under a table. Kind of looking at the effectiveness of that, and more generally speaking, how do things like shielding, radiation shielding effects mitigate the dose that we may get from this prompt radiation from a nuclear weapon detonation? So let's start with biological effects. So right here on the screen, you can see there are two generic illustrations. The one on the left is, just call it a cell, some generic cell. And the one on the right is a representation of a DNA strand. Now, there are three different regimes that we're concerned about when we're talking about radiation damage. The first is something called direct damage. And this is where our ionizing radiation comes in and interacts directly with some critical part or some structure of something like a cell. Cell wall, the mitochondria, the nucleus, anything. Now, what happens is when our radiation comes in, it can directly ionize the molecules of these structures. When it does that, these molecules can then recombine with things that are around them, or the free radicals we're going to see that are going to be produced through indirect ionization. And they're basically going to destroy the structure. If enough pieces of it or enough parts of it get affected, we can destroy critical parts of the cell. When this happens, of course, we undergo cellular death. So, no bueno. Now, the second is the indirect interactions. And this is our ionizing radiation coming in and interacting with the cells are 70 to 80% water. They're interacting with the water that's contained within the cell. Now, I can do this two ways. Well, kind of one way that results in two different outcomes. If something like a gamma comes in and it punts an electron off of an H2O molecule or water molecule, it now creates an H2O plus, or a positively charged water molecule. Now, this does not stay just as a positively charged water molecule. It undergoes, it splits apart, it decays, into a positively charged hydrogen and a neutrally charged OH molecule. Now, that electron that it punted off, it can then be attached to a different H2O molecule, creating an H2O minus, which again undergoes subsequent decay and becomes a neutral hydrogen atom and a negatively charged OH molecule. So you're probably thinking, well, great, what does that mean? Well, those two molecules can recombine not only with themselves, actually all the constituents of these molecules can recombine not only with themselves, but other things that are within the cell, including something like molecular oxygen, or O2. So what happens is this recombination can result in two very highly reactive chemical species. And this is hydroperoxyl, which is HO2, and hydrogen peroxide, which is H2O2. Now, some of you may remember when you were kids, one of the things that your parents may or may not have done when you got something like a cut or a scrape is they would pour hydrogen peroxide on it, and you'd see all the fizzing, and they would assume, and they probably told you, that it was killing all the bacteria and the bad things that may have gotten into the cut. In actuality, the hydrogen peroxide was just basically killing everything, including your own cells. Now, it wouldn't have been too bad, it doesn't penetrate too deep, but hydrogen peroxide and this hydroperoxyl, they interact readily with so many different molecules, and basically what they do is they end up destroying structures, cellular structures, by very similar to what happens with direct ionization, which is they attach to something that's kind of important and they kind of rip it away from the structure that it has been a part of. And in this way, we can get this indirect damage through ionization of water interacting again with critical parts of the cellular structure. And when too much of this happens, of course, again, cellular death occurs. Now the third one, and I'll come back to this to what happens within the cell with these different chemical species. Now the third one is this long-term damage, and long-term damage, for all intents and purposes here, we're going to assume is talking about damage to DNA. Now DNA, the strand I've got here shown, DNA has basically four components that are connected through these sugars. So we have adenine, thymine, cytosine, and guanine. Or if you've probably seen, like in some of the movies or maybe in a TV show, when it shows genetic code, they just use the abbreviations for the letters of ATCG. So how does ionization or how does incoming radiation affect DNA? Well, with ionizing radiation like gammas, what it can do is it can come in and it can ionize sort of the bonding area of one of these adenine, A, D, C, or G molecules, and then so it can bump off like a hydrogen, and that hydrogen can now go reconnect with something else. The long and the short of it is we end up with one of these that now looks like something completely different, so that when it comes time for cellular replication, which involves taking that DNA, basically unzipping it, and then replicating it so that you can make a new cell, now you have a piece of it that's not going to replicate the way it should because it now looks like something else, so it's going to attach in a different way. And now we're creating defects in DNA through the replication process. Now, if you get enough of these, or if they're in critical junctures, what that means is as cells reproduce, they don't reproduce correctly, which means they either don't engage in their intended function, or they function at suboptimal levels, or it creates something completely weird, like that's definitely not working as intended, something like a cancerous cell, which can be have an incredibly rapid cellular regeneration rate due to changes in its DNA. So that is sort of long-term effects of what can happen when radiation interacts with biologic systems. So we can get interactions with cells themselves, either through direct or indirect, which can result in the destruction of the cells, or we can get interaction with something like DNA, so that when cells replicate, it doesn't go quite as intended. So we either get dead cells or cells that reproduce incorrectly, resulting in a whole host of problems, including cells that are alive but don't perform their functions, cells that, because they're constructed incorrectly, don't actually live very long, just die almost immediately, and various other permutations. Now, I said I would come back to direct and indirect, well, mostly indirect, when talking about the effects of ionizing radiation on a cell. So I'm going to grab my little pen here. So what we can see is, imagine that most of this area, let's just say that's a whole lot of water, okay? Now imagine that we have an incident gamma ray. Okay, the gamma ray comes in, and we get an electron here, it scatters, goes this way. We get an electron here, it scatters, it goes this way. We're knocking electrons off and creating these positively charged particles. Okay, and then it can go out of this little volume and do it again, and then finally it can scatter out, or it can be absorbed via photoelectric effect. Now with the gamma, the higher energy gammas that we expect from prompt radiation, these are going to distribute their energy and cause ionizations kind of over a pretty long path through something like a cell. And because of this, the recombination that's necessary to form these caustic chemicals, they don't occur all in sort of one location. they're spread out so that the amount of damage that they can do becomes kind of minimized. Now, if you have a very large amount of something like gamma rays incident on a singular cell, sure, each photon is only going to cause, these sporadic interactions and highly distributed formation of these ions. But if you get enough of them, eventually you're going to create high concentrations, which will result in damage to the cellular structures and ultimately cellular death. Now, I know we're not really considering this as part of the prompt radiation coming from a nuclear detonation, but we're going to see this more when we talk about delayed radiation coming from a nuclear detonation. Now, imagine instead of this gamma, we had something like an alpha particle, and the alpha particle comes in and it dumps all its energy right here, very, very close together. If we recall on, whoa, what happened to my slides? Okay, I'm probably going to have to cut that out. So if we recall, when we talked about the interactions of charged particles, these heavy charged particles, they don't travel very far. They interact very heavily via the Coulombic forces. Okay, so they're basically just punting these electrons away from whatever they happen to be bound to, and they stop in a very, very short distance. So what this means is we've now created a ton of these ions, which are also called free radicals. If you've ever heard that expression, this is what it means. It means these ionized pieces of water that are floating around. And these free radicals recombine so that they're not free anymore. Anyway, because of the clustering or the ability of a heavy charged particle to dump all of its energy very closely, what we end up seeing is a large concentration of these very caustic molecules confined to a very small volume where they can do quite a lot of damage to whatever part of the cell happens to be nearby, be it the cell wall or the nucleus or the mitochondria or something like that. So again, while it's not super relevant with the prompt radiation, it's important to note that this is the mechanism by which these heavy charged particles like alphas or protons can actually do way more damage than something like gamma rays ever could. The only way gammas become dangerous is if there's a lot of them interacting, again, with a small volume like a cell and creating a lot of these free radicals, which can then recombine. Now, neutrons are a bit different. So this ties into the heavy charged particle problem. So when a neutron comes in, it doesn't interact with electrons. So it doesn't create this ionization that we would normally see with something like a gamma photon. What it does instead is it'll slam into a hydrogen that's attached to something. More likely than not, it's going to be one of the water molecules that's within the cell. And now it's going to create an energetic proton, which is a heavy charged particle. Now, the proton doesn't dump its energy nearly as quickly as a heavier thing like an alpha particle or a fission fragment, but it does tend to produce a lot of ionizations along a pretty short path. So where our alpha kind of looks like this, what we can see is a neutron coming in and scattering out. But now we have a proton that's coming in like this, and its path length is going to be a bit longer than the alpha particle. But again, it's going to be confined to a much smaller volume than what we would see with a gamma. So when we talked about quality factors, and we talked about the different types of dose, and the reason that we rate gammas differently from things like alpha particles and neutrons, this is why. Neutrons create heavy charged particles which can very much concentrate their energy deposition, very similar to alpha particles, which is why the quality factor associated with neutrons and heavy charged particles is much higher than the one that we see with gammas. So hopefully that ties all that together. Very similarly, unlike the ionization damage that we can see with DNA from something like an incident gamma, when a neutron comes in here, the neutron can just straight up knock a hydrogen off of the end of one of these base pair molecules and make it look like something else immediately. So it doesn't have to undergo ionization and then the molecule decays into something else, or something attaches to the now ionized part of that molecule and rips it away. No, the neutron can just straight come in and break remove one of the hydrogens and essentially just break the strand bond itself almost immediately. And there's something called a single strand break and a double strand break that can occur with both neutrons and ionizing radiation, where if we look at these connections, there's single strands that connect these two molecules here. And so we can come in and break one of them because of, again, the direct ionization, indirect ionization, or through a neutron just smacking part of it off. And that's bad because then it recombines in weird ways. And we also can do a double strand break, which is probably even worse, because unlike where, maybe one of these molecules kind of looks like a different one, so it's recombining when the cell undergoes mitosis, it can recombine slightly differently. If you get a double strand break, then what you can get is you can get some weird three-dimensional recombinations, making whatever it produced completely non-viable. So that's kind of how this radiation is interacting with biology to induce damage, both in the short term, and then if we're talking about DNA damage, in a bit more of a long-term scenario. Okay, so what happened? So this particular graph is from the lecture notes, and it's looking at radiation exposure to what I'll just call the GI tract, the throat, the esophagus, and the intestines, really, the stomach, intestines. Basically anything that's involved with processing food. And what we're seeing here is kind of what can happen as a function of dose with some relative probability. So what we see here on the vertical axis, and I thought I should explain this one because it's a bit more intuitive than the other figure that precedes us, talking about how different cells respond to radiation. That one is just there as an example. This one actually conceptually is a bit easier to grasp. And this is the incidence, or the percentage of the population that these different systems symptoms are going to occur in as a function of our radiation exposure. Hopefully that makes sense. So what we can see is starting here at about the upper 30s, and here the units are in centigrade, but if you recall, centigrade directly corresponds to rads. Okay, so those two things are directly equivalent, so this could actually be in rads and it would still be the same. So what we end up seeing here is several lines that we have a legend here that shows us anorexia, that is the lack of desire basically to eat, or to eat and then vomit. We have nausea and vomiting, separate categories. Anorexia, this diagram's kind of weird because anorexia is a psychological condition, not necessarily a physiological condition, but we'll ignore that one from now. You could probably just ignore that A for all intents and purposes. So we have nausea, vomiting, diarrhea, fatigue, and then we have some extensions to these lines, which are considered normal for whatever that exposure happens to be. So what we can see here is, if we look, fatigue is the thing that starts to show up at the highest level. So fatigue doesn't occur until fatigue occurs kind of before we start seeing this anorexia line. So if we discount the line, fatigue is the first thing that we'll see in terms of dose. And we see it at pretty high incidence. About 20% of people exposed to, we'll call it about 40 rads, will start to exhibit fatigue syndrome symptoms. And that starts increasing up until we get about to 300 rads, and then it increases dramatically. The next one that we're going to see is nausea, which doesn't start until about mid 40s for the rads or centigrades, And then we don't really see an appreciable response until about 10%. And by then, we're already up to 60 rads or centigrades. And then, of course, this continues on and sort of peaks at 95% of all people will show this effect at about, I don't know, what do we say that's it? About, we'll call it a little more than 400. Yeah, we'll call it a little bit more than 400 centigrades or rads. And then you can obviously read the rest of the chart. So what this is showing for exposure to our GI tract, we can see these deleterious results with as little as 30 to 40 rads, and they increase in the percentage of people that will start exhibiting these symptoms quite rapidly as we move up in dose. So one of the things that's very popular to show in movies and TV about radiation exposure is, vomiting blood, bleeding out of orifices, eyes, and that sort of thing. The vomiting blood is coming from basically damage to the GI tract, to the stomach lining, to the lining of the intestines. Well, that's more bleeding out the other end. But damage to the esophagus, anything that's connected to the GI tract that, when you destroy it, produces, basically ruptures within the structures, which then, allows blood to seep out. And that's what causes the throwing up the blood. And, you can also get that in various other bodily systems. But it's a very, sort of famous trope with radiation, acute radiation exposure. And as we can see here, it does have some merit. So how bad can it get? So that was just for one particular system with throughout those several different categorizations that we saw in the last lesson for how sensitive these different overall organ systems in humans are sensitive to radiation. So let's look at this cool little chart. Summary of clinical effects of acute ionizing radiation doses. And acute means short term, as opposed to chronic, which means more in the long term. So we have 0 to 100 REMS. Now we're talking REMS instead of RADs, so we're getting into, these are specific to our different biological systems. So we've added that weighting factor to account for how sensitive certain systems are than others. So we have subclinical range, 0 to 100 REMS. So this would be 0 to 100 centigrade, which we saw on the previous chart. So vomiting, none. Onset, nothing. Leading organ, hemopoietic tissue. Then we have gastrointestinal tract, central nervous system. These are things that are affected. So characteristic signs, again, below 100 REMS, below 50 REMS, really nothing. No critical exposure period. Therapy, reassurance, pat them on the back and tell them they're okay. And then prognosis is excellent because nothing happened. And then no convalescent periods, no death occurring, etc. Now let's go up into what's called therapeutic range. Now this is for radiotherapy used for treating things like cancer. So we have 100 to 200 REMS. Now the reason this is like therapeutic is because this is experienced in a much more controlled environment where they have seen very precise doses administered to different types of tissue, and they can definitely see what the outcome is, as opposed to the only sort of exposure that we have to prompt radiation from nuclear weapons comes from two very specific incidences, and we didn't have the information that we have today to analyze the survivors of both Hiroshima and Nagasaki. So that's why we're using clinical ranges, because this stuff is much more precise and has been experimentally determined and then theoretically modeled. So we have 100 to 200 REMS. This is clinical surveillance range. 200 to 600 they call effective therapy. And then 600 to 1,000 they call promising therapy. Don't ask me where they came up with those names. So incidence of vomiting, when you're down to between 100 and 200 REMS, it's, and these are, we can call this centisievert. Infrequent at 100, more common at the upper end of that, 200. But if we move into effective therapy, so at 300 REM, everybody throws up. And then from 6,000 or 600 to 1,000, obviously, if 300 is the threshold in the previous category, again, we're going to hit 100%. Everybody's going to throw up. Now, if we move down to when does this occur, 3 to 6 hours for the lower the lower exposure, half an hour to 6 hours for the mid-range exposure, and then very, very rapidly, which is between 15 minutes and 30 minutes or half an hour for 600 to 1,000 REMs. And then how long does it last? Well, less than a day for the first part, 1 to 2 days for the mid bit, and then 2 days for the second part. Latent phase, this occurs after the initial treatment has been administered. So after the initial radiation has been absorbed into whatever particular system, and we have this happening days later and lasting for weeks, except in the case of the lethal range, which obviously if it's lethal, and we'll talk about the lethal range here in a second. And then we have final phase, which is much further in time down the road, measured in weeks and possibly months. So, hemopoietic tissue, you don't see any signs of anything occurring. In the lower end, we kind of see moderate leukemia. In the higher ends, severe leukemia, hemorrhaging, infection, some other words I don't know. So bad things. And then critical post-period exposure is 1 to 6 weeks for the middle and high range of therapeutic doses. So from 100 to about 1,000, 200 to about 1,000 REM. So you're going from centisievert all the way up to a sievert. And then what's the therapy? What's prognosis? Well, once you get into the 200 REM category, it doesn't look quite as good. So they list that as guarded, which means they want to be optimistic, but there's a chance you're going to die. And then finally, cause of death, if you do die. So what's the time period of which you may expect to die because of this? I know I'm making very light of this subject, but otherwise it would be very grim, and I don't do grim. So convalescent period gives that time, and then what is their expected incidence of death, which is why we have that guarded prognosis. We see 0 to 90% in the mid-range, but 90 to 100% in this upper range. And you're probably asking, well, if they're almost always going to die, why would you even do that in a clinical setting? Well, this is what's called aggressive radiation therapy, and this is for things that don't respond to the lower levels. So, if the thing that they're trying to treat with radiation is going to kill you anyway, some people do elect to go in for this promising therapy regime where a large amount of radiation is introduced into the body. It's kind of a killer cure thing. So it either works or the outcome is the same as it was going to be before. I know, again, pretty grim, but this is the reality of some types of radiation treatment. And then finally, what's the cause of death? And from what we saw before, the characteristic signs, we have hemorrhaging, massive hemorrhaging. That is, we're destroying cellular structures all throughout the body, cause of massive bleeding, internal bleeding. So loss of blood means loss of oxygen, which eventually means loss of life. And then we have infections that can be produced because we've damaged things like our white blood cells or our lymphocytes or our body's ability to fight off external infections, and those infections will then go on to kill you because your body can't fight them off. So they will basically, bacteria and viruses will come in, colonize your body, and eventually shut down all of your biologic systems. Either through neurological means or through simply just destroying cellular tissue. So now let's look at like things that aren't even considered for therapy. Ranges above a sievert or 1,000 rem. So we have 1 to 5,000 rems and then over 5,000 rems. And this is the regime that's called palliative therapy. And palliative therapy is just simply making people feel better until they die. That's all that means. And again, the whole reason that we're looking at this from a medical perspective is because this is where we have precision measured doses and evidence of what occurs at these dose ranges. Not really studied with nuclear weapon output. So we have, again, 100% incidence of vomiting. Onset phase is between 5 and 30 minutes. Over 5,000, it's immediate. Same with the latent phase, the final phases. Anything over 5 sievert, it's all going to happen almost immediately on a very, very short time scale, seconds to minutes. Whereas in the 1,000 to 5,000 rem, depending on how the exposure was, what systems were affected, you can 5 to 30 minutes. So you can get duration in terms of days and latent onset days going out to weeks, and then days kind of maxing out at about 10 days. So what's the leading organ that's affected with these kinds of exposures? We have the GI tract, esophagus, mouth, your stomach, your intestines, all of that is affected here. And what do we get characteristically? Diarrhea, fever, electrolytic imbalance, critical post-exposure period. So when do you really need to be watched? Between 2 days and 2 weeks. Maintenance of electrolytic balance, so you get to drink Gatorade. The prognosis, again, is hopeless. That means they're going to die anyway, and that's the definition of palliative care, which means it just makes them feel better while they are dying. And generally speaking, the way that they expire is due to circulatory collapse. However, if you go over 5,000, what ends up happening is the respiratory system fails, your autonomic systems fail because you have massive damage to your nervous system. So, pleasant, I know, but this is something that is very important when we talk about radiation coming from, ionizing radiation coming from a nuclear weapon detonation. We looked at what can happen with thermal effects. We looked at what can happen with blast effects. And now we're looking at the truly horrific results from, radiation produced from that weapon. And this is prompt radiation. We still need to correlate what's going to happen in the long term with these biologic effects. And I think that's going to be the next section or the next lesson that we'll cover. So, dose lethality. Some of you may have heard of the term LD50, which that's a shorthand term for lethal dose of whatever in 50% of the population. Now that can be further expanded upon by adding another number, something like LD50-60, which is lethal dose in the population, 50% of the population after 60 days. Now what we're looking at here is, surprisingly, LD something in 60 days. Now this comes from a National Council on Radiation Protection, which is different from the International Council on Radiation Protection. Just believe it. No, it really is a thing. And this comes from a report number 42, which is titled Radiological Factors Affecting Decision-Making in a Nuclear Attack. Now, you can go ahead and buy this. It's not available freely. They charge for these reports. I think it's $16, $8 on Amazon for, I think, a used paperback copy. Anyway, this report came out in 1974. So the axis for exposure is in REM. So what we're looking at here is how many, what's the incidence of lethality on the population in terms of radiation exposure, ionizing radiation exposure. So we see for 5% of the population to die after 60 days, it's a little bit above 200 rem. 50% of the population, however, will do it at about 450 rem will expire. And then finally, 95% of the population will perish after about 900 rems, or less than a sievert. Now, if you recall, this is actually in the therapy range that we saw. The main difference is with this particular figure, this is for what we call whole body exposure. So this is all of your systems being taken into account. So nervous system, GI tract, renal systems, lymphatic systems, all of that. And then distributed as the weighting factors that we saw from the last lesson. Whereas in the therapy case, it can be particularly, the radiation can be targeted very accurately to a very small volume. So what you may see is, where where clinical exposure to radiation targeted to very small volumes for something like a cancer can have very good prognosis, even though they're in that 200 to 600 range. Whereas, whole body exposure becomes a bit of a different story because much more, many more critical systems and highly susceptible systems are exposed now to the same amount of radiation instead of being confined to a very small volume. Now, this comes from the Army Field Manual FM 101-31-1. And this is looking at dose in rads. I think this is tissue equivalent dose, to be specific. And two different, types of activity for people. One is for people that are involved in physically demanding activities, like I don't know, running or wearing a lot of gear and marching or something like that. Something that causes a high degree of physical stress. And then we have the other ones, which is physically undemanding, which would be something like a desk job, or a couch potato or something. And the reason I included this because it's pretty interesting. So the Army says time after exposure and the dose that they're getting, we have no symptoms. Functional impairment, temporary incapacitation, permanent incapacitation, and death. So the takeaway here is that for no symptoms, it's about the same, right? So we're looking at, going from immediate to maybe, 4 or 5 hours, all the way, up to a little bit over 1,000 rads tissue equivalent. No symptoms at all. If we move up our dose between, whatever that number happens to be, to about, I want to say that's probably going to be about 3,200, 3,300. We have functional impairment on the physically undemanding, but at that same range where we're at this dividing line here. If we look at physically demanding, we're already into the incapacitation range in this very short time period. Now, they kind of sort of level out themselves to where if you're a couch potato, if we look at time after exposure, we're into functional impairment all the way out to a bit more than a month. But following that, you kind of get death. Excuse me. So it ends up the same for both of them. But if you're a couch potato, you don't suffer permanent incapacitation until much higher doses. If you're doing something physically demanding, of course, all of these things are lowered quite a bit to where you get permanent incapacitation right around 8,000 rads, where here it doesn't occur until more than 18,000 rads. So why does it look like this? Well, the more physically active you are, the more physically demanding your activities are on your body, the more your body is going to have to replace cells that expire because they're working overtime. So whenever you're losing a lot of cells because they have to be replaced, if you add that to the cells that you're losing due to direct or indirect damage from ionizing radiation, you're losing a lot of tiny bits of you are dying, much more if you're extremely active than if you are inactive. Now, eventually, it all sort of washes out the same, where death. We have death occurring, with certain exposures at certain times, and they're pretty much the same either way. So this is just showing that if you're exposed to radiation, right, like extreme amounts of radiation, then your best bet to minimize your symptoms is to kind of not be active. You're much better off being a couch potato, where you can maybe have temporary incapacitation versus permanent incapacitation, or functional impairment, instead of temporary incapacitation. So shout out to couch potatoes. If you get exposed to ionizing radiation, keep on being a couch potato. It's probably better for you. Okay, so that's kind of looking at biological effects of radiation. So this next section is we're going to talk about radiation source terms. That is, how do we characterize the radiation coming from a nuclear weapon detonation, the prompt radiation coming from a detonation. So I'm going to pause here for a second. And now we're going to continue. So let's look at neutrons first. How do we characterize neutrons coming from our detonation? Well, we know that we can have two different kinds of neutrons, right? That escape from our fission chain reaction, that don't actually do anything and leave the system, as it were. So we have fission neutrons, and we also have fusion neutrons. Now, if we want to categorize how many neutrons are coming out of a given type of weapon just due to fission escaping neutrons, we can look at it this way. This cool little equation here that has some numbers, has some Q values, but the biggest one that's impacting here, because this comes directly from the generational calculations that we did previously to figure out how many neutrons are we ending up with, like per kiloton. This is how many neutrons on average are produced per fission minus 1, or that nu minus 1. And that's the number of neutrons per kiloton. Fusion, we have a little bit different because of the way that we can calculate fusion neutrons, but here it's just kind of focusing on DD fusion, so producing those 2.45 MeV neutrons. And we get about 25 MeV per 2 neutrons. That's not DD. That's, if you think about it, that's actually that combination, if you recall, of the whole of DD and DT fusions that can occur if they're both present. So that's why that number looks a little bit different. And then we have number of neutrons per KT or kiloton from DD fusions. Again, it's not really the whole picture, but it is a way to kind of quantitate what's going on. So let's look at this table. Source neutrons per kiloton of yield. So we have uranium, plutonium, and then we get into our fusion fuels. So let's look at uranium. Maximum number of neutrons available for escape per kiloton. Remember that L term, our loss term? That's what this is pretty much saying. And then typically, of those that aren't interacting to cause more fissions, of those, how many of those can actually escape and not interact with, like, the case material, the gold and the iron, and being absorbed by, the uranium-238 in the case of, if it's present, basically neutrons that can escape without interacting. And that's about 50%. So the net number of neutrons that escape per kiloton for something like a uranium weapon is about 10 to the 23rd neutrons. For plutonium, we're producing slightly more neutrons, slightly less of them are going to get out, but overall, we're at about the same, 1.1 versus 1.3 times 10 to the 23rd. So this is the neutron flux that we can expect emanating from a fission weapon. It gets more complicated when we look at fusion because we don't really have any data for some of it. When we look at just DD fusion, right, we have 10 to the 24th neutrons available for escape. We have no typical escape fraction, and we don't know how many net neutrons per kiloton of weapon yield can we get from this. So we're missing 2 out of the 3 pieces of information. Not super useful. Now, if we look at 50% deuterium, 50% uranium, think boosted, perhaps. We get, again, 10 to the 24th neutrons available to escape, because remember what happened when we threw all of those fusion neutrons in. However, only about a quarter of those are actually going to get out. It has to do with the energy distribution. But from this, we can figure out, okay, for something like a boosted weapon, we could get about 3 times 10 to the 23rd. Again, same order of magnitude as we see for a pure fission weapon with no fusion component to it. And then finally, for DT, we know how many neutrons can escape, but there is no available data for what percentage of those actually do escape and then yield per kiloton. Because in DT, you're looking at a thermonuclear weapon for the most part. So our neutron sources are a bit harder to characterize when we move out of the pure fission weapon realm. If we're just talking about fission weapons, though, we got you covered. Now, neutron spectrum. This is the neutron energy spectrum, or the Watt spectrum, that you saw before when we talked about fission. Except this is on a different scale. This is on a log scale. And again, this is showing neutrons produced per kiloton in certain energy ranges. It's basically the same thing. This is experimentally determined, which is or determined through something like Monte Carlo modeling, which is why it has discrete energy groups and isn't that nice continuous line that we saw before. So what's this telling us? Well, it looks like a fission neutron spectrum. That's what we're going to see. We're going to see a lot down at the lower end, and it's going to taper off at the higher end. Where this does differ a bit from what we saw with the Watt distribution is, for one, this doesn't go down below 100 keV, so we don't see the drop-off. So that's one thing. The other thing is this spectrum can be slightly modified due to some collisions that are occurring with neutrons. They may be escaping, but they may hit things on the way out. So we should see and do see a slight energy shift. Won't be really apparent to you guys, but I just wanted to make it known to you that the neutrons, some of the neutrons are going to hit things on the way out and not going to transfer a whole lot of energy, given the average Z of the nuclei they're going to encounter on the way out. But we will see a slight shifting down into the lower energy spectrum. But now this is for just pure fission, and it looks like we kind of should have expected to look. However, if we look at something that contains fusion, we see an uptick. And we see an uptick at the higher energies. And this specifically is for DT fusion. And the reason I know this is because this uptick is right around 14 MeV, which is the energy produced by DT fusion, the neutron energy produced by DT fusion. So what this is saying, with something like a thermonuclear weapon, we don't see the drop-off at the higher energies nearly as much as we see with pure fission. But in fact, what we see is this peaking of high energy neutrons at the upper end, where we wouldn't see anything for a normal fission device. Now, why is this important? Well, neutrons interact based on their energy. So higher energy neutrons are less likely to interact, or if they do, are less likely to dump a whole bunch of their energy in any singular collision, with the exception of something like hydrogen. So the long and the short of it is, because the probability of their interacting goes down, they travel a whole lot farther than just neutrons created from pure fission. So we have these two different energy spectrums. The one we really are concerned about when we're talking about radiation exposure to prompt neutrons, this is much more concerning because these neutrons are going to travel a much further distance away from our detonation point than we would see if there was no fusion component. Now, the gamma ray sources, as I mentioned in the previous lectures, there's something called prompt gamma rays. And sometimes it's misleading when you try to find out what exactly is the definition of prompt gamma rays. It says they're produced in the fission reaction. That's not true. In fact, what happens on these very short timescales, nanosecond timescales, is that our fission fragments, they're given kinetic energy, but they also are in an excited state. And they immediately de-excite by emitting gammas. Now, this is differentiated from delayed gamma production, which is these fission fragments undergoing further successive things like beta decay and producing gamma rays at the same time. So, to be clear, prompt gammas don't come from the fission reaction itself. They come from the excited states that the fission fragments are produced in. Now, as I mentioned in the previous lecture, a lot of these don't ever get out of the environment of the weapon. They're going to interact very strongly with the high Z materials, the bomb casing, the whatever remains of the weapon fuel, and other things that may be contained within the weapon casing. So only about 1% of those escape, and gammas only carry about 4% of the total energy. So 1% of 4% is a very small fraction of the energy per fission event that are carried away. Now, delayed gammas, as I mentioned, this comes from the subsequent radioactive decay of the fission fragments. And these can be rather lengthy decay chains involving, anywhere from 2 subsequent decays all the way to something like 8 or 9 subsequent decays before they hit a stable isotope. So, and this is produced after everything's basically been vaporized. Now, we can get another type of gamma ray, which is not the delayed gamma rays from the fission fragments, but something called neutron capture or radiative capture. So remember, we saw that only a certain percentage of the neutrons were going to make it out, of the ones that were available to make it out. And I said that they would interact with things that were already present within that, we'll call it the debris region of the weapon. Those neutrons can be absorbed and be captured by other nuclei. And radiative capture means that we have a nuclei that sucks up a neutron, becomes an excited nucleus, and then de-excites down into a stable mode by emitting a gamma ray. So this is called radiative capture again, and this can happen with anything that's present within the confines of the weapon itself. We can also have inelastic scattering. Inelastic scattering is kind of related to radiative capture, where radiative capture, neutron comes in, gets slurped up, and then we see a gamma ray go out, and that's it. And then further down the line, it may be radioactive. We may see a subsequent decay. That's later. The other thing that can happen is a neutron can get slurped up, deposit some of its energy in the nucleus that just ate it, and then it gets spit back out. This is called inelastic scattering. And it's basically a neutron comes in, becomes part of the nucleus, and then leaves again, but some of its energy has been retained by the nucleus in the form of excitation, which it then gets rid of by emitting a gamma ray. And then the decay of fission products, which I've talked about, so I don't think I need to further expound on that. So we can get what we expect, which is the radioactive decay of the fission products that we've made, but we can get that radiative capture, which you maybe wouldn't expect, and then we can also get inelastic scattering. And inelastic scattering, the neutrons are still there. We just are getting gamma rays in addition to the neutrons. And this is just the kind of an energy spectrum for gamma rays coming from fission, from prompt fission. And it kind of looks like our neutron energy distribution that we saw before. And we have things that say extrapolated because it's really hard to measure lower energy gamma rays at some distance away from some a fission event that's producing them. You're either overwhelming your detector or your detector's far enough away so that you don't really get that high of a signal compared to the higher energy ones that make it much further. So that's why it's got those little extrapolated lines. I can tell you from experiments that I have been involved with myself with measuring gamma radiation from a critical fission assembly, is that at the low end you have to take some serious precautions and mitigation effects in order to not overwhelm your detector because of the number of these low energies that are interacting with your detector. And it just sort of overwhelms it. But yeah, this kind of looks like our neutron energy spectrum that we talked about before, peaking at around 0.8, 800 keV to about 1 MeV, average energy of about 1.5 MeV. I would have to guesstimate. So we're looking mostly at the gammas that are going to get away are going to be more likely in the high energy regime because they'll be less likely to interact, and if they do interact, they'll be less likely to lose a significant amount of their energy via something like Compton scattering. Okay, so that's coming from the weapon itself, but we can make gamma rays outside of that. We'll call it the weapon environment because that sounds better. These are called secondary gammas, and these are produced by neutrons interacting with stuff in the atmosphere or in the air. And most importantly, we have nitrogen, which comprises a very large percentage of our atmosphere. And neutrons will interact with normally occurring nitrogen to produce nitrogen-15, which will then de-excite. So we have a radiative capture event, and we have the production of gamma rays from atmospheric nitrogen caused by the neutrons produced by our nuclear weapon. It's quite a convoluted chain of events. What's interesting about these secondary gammas is they can be way more prevalent than the prompt gammas coming from our fission. Because remember, not many of those ever make it out. However, the neutrons do make it out. They interact with the atmosphere, and they can create a large amount of gamma radiation that you would not expect if you were just looking at the weapon itself. Now we have the time dependence of our gamma energy. So if we had that magical camera that could give us snapshots at various whatever time intervals that we were looking at, this is what we would see. We would see the prompt being produced in the nanosecond, tens of nanosecond range. And then as we move forward in time, we would start to see inelastic scattering from neutrons producing more gamma rays. And then we would start to see decays from isomeric decays. This is from other excited captures, radiative captures within the weapon material itself. And then finally, as we move further out, we get the nitrogen captures in the atmosphere as those neutrons are streaming away from the detonation point. And then finally, on the longer scales, seconds out to minutes, to days even, then we start seeing the radioactive decay of those, further radioactive decay of those fission fragments that did not occur at the very small scales that we consider to be prompt. So that's characterization of our prompt radiation sources from a nuclear weapon, both gammas and neutrons. So this last topic that we're going to cover is going to be radiation dose and shielding. Now what I think I'm going to do here, given the limits, the upload limits, even for YouTube, because I'm currently at 59 minutes for this, is I think I'm going to take and cut this part and put it in its own separate video so that, the time stamp for the halfway point. In this particular video will be below the video, but if you're listening to this, you've already made it all the way through. So this next part will be made into its own separate video, and it will be posted on the same page.